Okay, so basically, like, we can come up with some hacks to try to address some of these failures that come about when we use ML systems in the real world. But of course, they do not always continue to work, and we still have these fundamental problems to work on. Another domain is self-driving cars, which again, we've been hearing a lot about, but where are self-driving cars right now? And in 2018, there was this really tragic incident where a woman was killed. And among other issues, a machine learning system failed to recognize a pedestrian who was jaywalking because it was only trained to recognize pedestrians at crosswalks. So I don't want to start this talk on a very dark note. So sometimes there are funny errors that can happen too. Like, for example, games can be ruined because models get confused. But the main takeaway is that we are at this interesting point where we see really impressive advances in certain benchmarks, and we see new things on Twitter each day, and it's really exciting because we want to use ML to solve really important problems. But at the same time, our systems are not there yet that we can actually use them in the real world and know that they won't break or do mistakes. And so in this talk, I'll talk a little bit about how we started thinking about robustness and how the questions have changed in the past few months. So what's the main thing that's going on here is, when we typically think of machine learning, what do? Is we collect a data set of examples, and we assume they come from some distribution P, and we split this into a train and test. So we train on the training data, and we evaluate on this held out test set. So most of our evaluation is on such test examples that look very similar or are drawn from the same distribution as the training data. And most benchmarks as well as theory are under this setting. And this is already quite challenging, and it's really hard to understand when and why systems work, even when the test examples are from the same distribution as the training data. But this is also insufficient if we try to think about real world deployment, because what the model could encounter when it's actually used is a wide range of examples, including those that might be outside the distribution that your training data was collected on. And so, my goal is trying to think about how do we evaluate and improve performance on a wider range of inputs that the model could encounter beyond just the set of examples that are from the same distribution as the training data. And so to think about how do we get this set, let's look for inspiration at a few examples. So if you look at self-driving car, this is what I was used to when I was driving in California, but then now I have to learn to drive in Pittsburgh, and hopefully self-driving cars can also do this. And so one kind of a setting would be that we want self-driving car systems to work reliably in all weather conditions, including like sudden inclement weather. And for example, if you look at crosswalks, we want to think, or pedestrians, we want to think about how they can be using a crosswalk. They can be jaywalking, they could be skateboarders, or from India where I come, like you could have cows on the road and so on. And so another way to cast what we would expect is we want to work well under all pedestrian activity and not just like a few, or this distribution that you've seen at training. And similarly, hospitals or healthcare systems should work well across all locations or all sensing equipments and all subpopulations or demographics, like, for example, the facial recognition system that we spoke earlier. And of course, sometimes people might also try to break your system. For example, in content filtering, you want to post toxic content online, and you as a person who wants to post toxic content might not try to stick to the same distribution that the model was trained on. And so that's another example where we want to think about like all adversaries that could be breaking the system. So across these examples, to me, the common thread when I was thinking about this problem was that we want to work well in sort of a worst case scenario, or like in all weather conditions, or all pedestrian activity, or all adversaries, and so on. So I was really interested in thinking about how do we improve performance in this like worst case kind of a situation, which goes beyond just looking at independent examples from your training distribution. So that motivated the robust ML formulation, where in classical ML, we have some training data from a distribution, and we only care about performance on new examples from the same distribution. But in distributionally robust machine learning, what we do is we define a wider range, like around the training distribution, for example, the set C of P. And we want to do well on all distributions within this set C of P, not just that one particular distribution P that you got your training data from. So if you visualize this, like you could think of your original distribution that you got data from as like one point, but you want to get good performance across a wide range of distributions around that. And so, by defining this set C of P appropriately, you could try to include things like multiple weather conditions or like different adversaries trying to break the system and so on. So, but this is like one kind of formalism to try to think about robustness, where we want to get good performance in worst case across a wide range of distributions, even though we have data from only one distribution. And so the initial approach to robustness that I had in mind was that let's try to understand the fundamentals of how do we achieve this for some arbitrary or like many arbitrary sets C of P. Like if someone gave you an uncertainty set that characterized what they wanted when it is deployed, let's figure out how do we design the machine learning algorithm to get good performance within this entire set. And of course, then there's a question of like, how do you actually get these uncertainty sets? But I felt like we could probably approximate real world distributions in some way. And this way we put the pieces together and we get a robust system. So my initial goal was, or like what a lot of people in the community as well were trying to do, was look at well-defined sets of uncertainty sets and try to get good performance to that, with the hope that the next step would be to try to get the right uncertainty sets for real world applications. But realizations over time was that every step that is getting robustness to even a very simple uncertainty set is actually really challenging. And you do compromise on your accuracy quite a bit. And so it's not as simple as just like composing multiple uncertainty sets. And it's really important that you get the right uncertainty set. And so it made me realize that maybe we should, like, instead of going from like fundamentals and then projecting the real distribution shifts on that, can we try to think about real distribution shifts directly? So that's what I'll talk about in this talk about, can we think about natural distribution shifts that arise in the world and try to tackle them directly? And what I hopefully will convince you is that like the past few months or like this particular time in machine learning is particularly suitable for tackling natural distribution shifts directly, where we don't have to necessarily rely on having a mathematical characterization of what we expect to achieve when we want a system to be robust. Okay, so with that, I'll talk about the first aspect of why this is a good time to think about natural distribution shifts, is because of the ability to pre-train on diverse data. So here's the pre-training setup. So typically you have a lot of diverse unlabeled data that the model is first trained on, and you have this giant pre-training step where maybe a company trains this model on as much data that they can get. And that's the first step of pre-training. You get this pre-trained model that you then use for your particular application in the second stage of what I've written here as adaptation. So you might decide to use this pre-trained model for a particular, say, image classification task. Then you take this pre-trained model and you adapt it to get your final downstream model that might be more specialized to a narrow distribution. So why this is interesting is that in usual machine learning, we would have only trained on the narrow distribution that we want the model to work well on. But now we have the ability to like actually use a model that has been trained on much more diverse and labeled data. And there is a hope that this model actually knows much more about the world and natural distribution shifts, that the model will actually be robust, even though we have trained on only data from one distribution. So consider a satellite remote sensing task. So where we have, say, training data from North America, where typically it's much easier to, in certain continents, like actually get annotations for what's going on using the satellite imagery and mapping it to what we know about the development states. But we want to train a model on North America and then use it in situations where we do not have as much data, for example, Africa. So this is an example of a robustness situation where we have training data from one continent, but we do want it to work across the world. So if we did standard supervised training, we would have only obtained in distribution or like the training data from North America, because that was all the labels that we could get. And if we train this model and then hope that it works on out of distribution or a new continent, it doesn't work that well. Like we saw in the beginning of the slide, models do not work very well when we test on new inputs that are different from the training distribution. But there is hope if we imagine that in the pre-training or the transfer learning setting, this pre-trained model has probably seen a lot about the world and potentially seen images of satellites or other things from Africa and knows a much richer information about what it means to understand satellite imagery. And now if we can harness the information from this pre-trained model and then get our categories or figure out what the task is based on data from North America, maybe this model can actually work well even on data that we don't have explicit labels from, like Africa, because the pre-training state has actually taught the model something much more diverse. So this is kind of the hope of why we would want to use pre-trained models and why they might actually improve robustness, particularly for distributions that you could not have written down mathematically. Like, it's really hard to say what it means for satellite imagery to change from one continent to another, but maybe the pre-trained model knows that just because it's been trained on much more diverse data. And in fact, like if you look at different robustness benchmarks, and pre-training is like the only method that reliably improves performance compared to any other training procedure that you could have thought of. And the more data you can pre-train on, the bigger the gains in robustness. And not just robustness, but even performance on the downstream task itself can often be improved by doing pre-training. And like this intuition that pre-training does work is actually holds up, and we see that it's one of the most reliable methods to improve robustness across several distribution shifts. So how do we think about pre-training and how to use pre-trained models, and how do we improve robustness, and where do these gains come from? So typically in machine learning, we only think about like the population, this training loss, and then how it does well on the test set. But now we also have to think about, when we get the pre-trained model, how do we adapt it? Or what is this connection between the pre-trained model and the tasks that you care about? And how do we actually use the pre-trained model? So all of these parts in the pipeline are actually important to think about. But in this talk, and that's the new part, is trying to understand how does the pre-trained model interact with what you want when you actually use the model for a different downstream task. Okay, so how do we leverage this information contained in pre-trained models? So one common method of using a pre-trained model is as follows. So let's say you have some pre-trained representations shown in orange here, and you want to use it for classification. You will introduce a linear head, or like some weights that take the representation and give you a prediction by applying a linear combination. And then you initialize the rest of your network with this pre-trained representation, and then use your standard cross-entropy loss, for example, and backprop through all the parameters here. So normal fine-tuning, what you do is you add a layer that gives you the classification performance, and after the objective, you minimize the training objective by backpropping through all parameters. An alternate approach could be where we do linear probing, where we do not change the representations. We assume the representations are really good, and we just learn a linear head. So the reason I mentioned these two things is, like, one way to start thinking about getting insights into how to use a pre-trained model is to first compare two existing methods or two natural methods and see if we can understand something about how this process should go, looking at how these two methods compare. Oh, okay, ignore this slide. So yeah, so first I'll talk about empirical observations, like how these two methods compare, and then we'll try to capture that in a theory setting that will give us some insights into what's going on and will potentially give us a better solution that we'll eventually test out. Okay, so we'll try to compare two methods of using a pre-trained model: fine-tuning and linear probing. In fine-tuning, recall, we update all parameters. And in linear probing, we freeze representations and we only learn the linear head on top. Okay, so I wanted to see what people think about how these methods compare. So the first task we'll look at, which is trying to simulate some kind of a natural distribution shift, is as follows. So this is a breeds data set where we want to classify an image into animal categories. And we train on one subset of the ImageNet hierarchy. So what this means is that if you look at dogs, like the training distribution has some species of dogs and the test has different species. So we have different animal categories, and we've split them into species that are seen during train and species that we test on. So there is some kind of a distribution shift. And this is natural because we can't really we don't have a way of mathematically saying what the shift is. And as a pre-trained model, we'll use a model that has seen unlabeled ImageNet images, including all these different types of animals. So the pre-trained model has been trained without labels on all different species, including the ones that we train and test on eventually. Okay, so is this setup clear? Okay, so the first thing that we'll do is just in distribution performance. So if we train from scratch, we get 92%. But if we actually use this pre-trained model, which has seen more data, you can do better. And so linear probing, for example, improves by a few percent, and fine-tuning further improves. So we see that fine-tuning, if we've updated all the model parameters, actually does better than linear probing. So let's think about out of distribution now. So how many people here think that linear probing, where we use a pre-trained model, will do better out of distribution than training from scratch? Raise of hand. Okay, so I guess most people, and you're right, it does do better than training from scratch, which is great. But what about fine-tuning? So we saw that fine-tuning did better in distribution than linear probing. So do you think fine-tuning does better out of distribution as well compared to linear probing? How many people think fine-tuning would do better? Okay, I guess it's a little obvious the way I set it up. That yeah, no. So linear probing actually does better out of distribution, even though in distribution, linear probing did not do as well. And this was kind of interesting because in most other like supervised learning settings, if you look at a model that does well in distribution, it's typically the one that does better out of distribution and natural shifts as well, because it's really hard to come up with a good robustness method for out of distribution when it's a natural shift. But here we actually see like there is some kind of a trade-off where something that works better in distribution actually works better, does worse out of distribution. Okay, let's look at another data set. We don't want to overfit to one example. So this is like CFAR10 classification, but now the train and test are slightly closer here. So the train distribution is the original CFAR10 data set, and the test distribution is a near replication of the entire pipeline that was done by Recht et al. So you can think of like people just decided to collect a new CFAR10 in 2019 following the same process that the original paper did. And again, we'll start with like the MoCo pre-trained model that has seen unlabeled ImageNet images. So like I removed the scratch because we've convinced ourselves, like, and I think it's like just universally true that linear probing and fine-tuning will do better than from scratch. So let's just compare these two methods. So for this data set and this distribution shift, how many people think linear probing would do better than fine-tuning out of distribution? So in distribution, like before, fine-tuning did better than linear probing. The question is out of distribution. Does anyone think linear probing would do better here? A few. The answer is no, because here the shifts are like so close and like there's such near replications that it's, this doesn't work. So it's not always true that one method is better than the other. So there's something to understand, like what is it about certain shifts and why does this behavior happen? Okay, so to summarize, like which method does better across fine-tuning and linear probing, so we did a more systematic evaluation over 10 data sets. And the common wisdom is that fine-tuning works better than linear probing because you can change all the model parameters there. And it's something that it's a de facto standard. It's like if you have enough memory and compute to do fine-tuning, you do fine-tuning. That's the usual wisdom. But actually, we find that for out of distribution, the reverse is kind of true, where fine-tuning actually does worse than linear probing on most data sets. So like this is an average over 10 data sets, but so yeah, on 8 out of 10 data sets, linear probing does better. But if the shifts are too small, then fine-tuning continued to do better. So the summary was that like while common wisdom says fine-tuning does better, we find that linear probing can actually work better, especially when you have a really good pre-trained model and you have large distribution shifts. For example, in the CFAR10 case, the distribution shift was small, and so that's why we didn't see this behavior. And like we can go into the details about these two methods, but the first thing that struck us was that this says that there's probably a lot we can do to improve downstream methods, especially with robustness in mind, because most of the common wisdom or heuristics that we have for using pre-trained models also just came from looking at in-distribution performance. And so if we were actually trying to use these models for robustness, maybe there's some more stuff to think about in terms of how we use these models. Okay, so I guess I promised like some kind of a theory setting that captures these empirical observations, so I'll try to do that. Okay, we can Anyway, so one thing to point out is that this is a little more tricky than normal analysis, because when we start with a pre-trained model, the downstream objective is basically the same, like whether you do linear probing or fine-tuning. You're just minimizing like some loss on your downstream labels. But the initialization, like the how you change the parameters is like actually changing things a lot. So it's really about the optimization trajectory. So it's not the optimization alone, but really like the non-convex objective that we need to understand. And so when we're looking at using pre-trained models, the unfortunate fact is that because it's really all about initialization and no longer about the downstream objective, we have to address this training dynamics, which is like generally very hard to think about. But we can still do some things like I'll show in this slide. Okay, so here is a very, very like toy intuition for what might be going on. So let's say that I'll show the in distribution data points in blue and the out of distribution data points in green. So let's assume we had really good pre-trained features. So by good pre-trained features, I mean that we have two classes, X's and O's. And so the features actually capture like some kind of semantic information about how these classes are related. So like the X's appear to the left of the circles, for example. But then out of distribution is like far enough. So there's no reason for the model to keep these two representations close. Like satellite images in Africa do look very different from North America. So they are like in a slightly different part. So let's see what might happen or what might go wrong when we start with a good representation and do fine tuning. So the first stage in fine tuning is we initialize a linear head randomly. So let's initialize this, say, this linear head. And when we like update the model, what happens is the features and the linear head both change in accordance with each other. So each time you pass gradients from the linear head to the features will change in a way to make the linear head good as a classifier. So for example, this is what will happen. So you start here and now your features will change such that the same head is like separating them better, and both of them will keep changing together. And so you might end up in a situation like this, where now your linear head has completely separated the training representations, but in the process has kind of changed the features so much that there's no longer this nice correspondence that we had between in distribution and out of distribution. So the simplistic assumption that I made here was that the OD features don't change at all in this process. And in practice, we observe that the out of distribution points change by an order of like 2 orders of magnitude less. So it is kind of true that because you're never updating on images from Africa, you're only updating on images from North America, the representations of of African images don't change very much, for example. So this is like a toy illustration of what might happen, where because you've initialized with a random linear head, it doesn't matter in distribution if the features also change, because we only care about how together they work, and they work well. But when we think about robustness, it's really important that the features haven't changed too much, because if they have changed a lot, then we have lost what we gained from pre-training on diverse data in the first place. Okay, so to complete the story, you can think about what does linear probing do. So linear probing, like by definition, doesn't have the problem that the features are distorted, because it just doesn't change the features at all. And so you just continue, like for example, you learn this linear head, you'll just keep this linear head, and it will work well both in distribution and out of distribution, but maybe it doesn't work perfectly because the representations might not be separated. For example, you might get a few points wrong, and that kind of is like the drop in distribution performance that we see when we do linear probing. So if we start off with a model that's not perfect, but still good, then fine-tuning actually makes the model better in distribution, but in the process has lost correspondence between in distribution and out of distribution, which is what we relied on for robustness. But linear probing, on the other hand, keeps the correspondence, but then loses the ability or flexibility to like improve the representations a little bit to make it better for the task. Are there any questions about this like toy illustration? Okay, so it's basically the same idea, but then we can make this more formal and like consider a general linear regression setting. And the interesting thing is that across all points in the training trajectory, right? So usually when I present this, people ask me like, can you just regularize the model, or can you early stop, and does that fix the problem? But we see that it's not actually the case. So across the entire, so this T here is the time step. So at any point in the training trajectory, you actually see that fine-tuning does worse than linear probing, given that features are high quality and that the distribution shift is large. Okay, so let's see if we can use this to get a better, like a very simple idea to get a better method. But so I showed you two methods, one that works well in distribution and one that works well out of distribution. And so natural question is, can you get something that does best of both? So to do that, like just to quickly summarize, like why did fine-tuning do better in distribution? Fine-tuning did better because the features might not be perfectly linearly separable for your task. And so by giving the model the flexibility to improve the features, you can improve performance. But it did worse out of distribution because you might have changed your features a lot to accommodate this randomly initialized linear head. And so if we want to, so the main, I mean, like the obvious method of getting the best of both is we do want to refine features, but we want to do them without distorting things too much. In other words, we only want to change the features if it really is important, not for like a reason that is the randomly initialized head, for example. So we want to make changes to the features that only those changes that improve performance on the task and that are necessary to improve performance on the task, because that way we can preserve maximal robustness. Yeah.
So does the second thing happen in the examples that you gave? So the CFAR versus the animal one. Does this happen?
I didn't follow. Sorry, CFAR was the second example. Animal was the first example.
CFAR was the one where
yeah. So in CFAR, it doesn't always happen, but this happens when the shift is large. So basically, remember the blue and green things, like if green doesn't change at all and blue changes a lot, that's when you have this danger. But if CFAR 10.1 is like they're both basically the same, so changing CFAR 10, like the blue will end up changing the green points as well, because they're essentially the same distribution, or they're very close to being the same distribution. Yeah.
The difference between pretests matter. I believe they matter a lot. Like you said, you were doing experiment on local too.
Yeah, we tried a bunch of different pre-trained models. We can try supervised pre-training on ImageNet as well, and like different. We didn't try MAE, but we tried a couple of different other contrastive methods as well. So this trend holds.
MAE reconstruction pretest tasks are very different from contrastive.
Yes. So I think when we said that like you need good quality representations, like I believe MAE, like linear probing doesn't work very well, so your performance is going to be like lower than fine-tuning there, but that's because the features are not like high quality enough for linear probing to work.
I see.
Yeah. But okay, so if we have a method that does better both in distribution and out of distribution, then we don't have to worry about how far things are and so on. That method will just always work. So that's the goal here. And so it's pretty obvious. So like if you want to modify features only as necessary, so let's go back to what happened with linear probing. Here, like if we learn this linear head and then we observe that the features are not perfect, then now maybe let's try to modify the features. And that is, we first learn a linear probe and then we fine tune. So the hope is that here, like by learning a linear head in the first step, we have done the best that we can with the current representations. And then we realize that it doesn't fit very well. And then let's actually fine tune the model now to make the representations better. So in this case, you're only changing representations because the best possible linear head didn't work well. Whereas if you had a randomly initialized linear head, you were changing your representations to just accommodate the random initialization as well. And so this is, I really regret this name, but the name we went with the paper was LPFT. And so you can actually prove that this two-step process of linear probing and fine-tuning can actually dominate both either method of linear probing or fine-tuning under a very simple setting. Theoretically, you can prove this. But then also, like, can we scale this up and see what happens? And so in this bottom row here is like the two-step process where you first do linear probing and then fine-tune. So now we see that we improve on both metrics like ID and OOD across every distribution shift and also on average. So this like very simple change to the process can actually get the best of both worlds. Just have the actual numbers, but that's fine. So I guess just to balance this a little bit more, we do find that the intuition that the in-distribution features change much more than out-of-distribution features is actually true. Like we just measure the L2 distance in perturbations, and we see that because you have not trained on OOD data, you don't change your features much. And by doing this two-step process, we also see that in-distribution features now change an order of magnitude less, because they now don't have to accommodate this random head that you had, and even though they still obtain the same training loss. Okay, so to briefly summarize this part, pre-trained models give large improvements in accuracy, but how we fine-tune them is actually key and important. Some of those differences don't show up just in distribution, but they really matter out of distribution because it's important to preserve whatever we learned about the diverse data to start with. And of course, the LPFT is just one. Is there a question? Okay. LPFT is just on one starting point, but like in general, there are many more lightweight fine-tuning methods and a lot of other new things that people have been coming up with. And these methods that don't change things too much are typically good for robustness. And of course, like theoretically, we don't understand like some non-linearities and deeper networks. And yeah, what's a broader class of adaptation procedures to think about? So because this talk is recorded, I didn't want to talk about some work that we have not yet put on archive, but sometimes really like small changes to the way you fine-tune your model can show significant gains. So you don't even have to use, for example, cross entropy, and you'll see a lot of difference, which again, you don't see much in distribution, but you see a lot of gains out of distribution. Okay, so with that, I'll switch to few-shot learning, but I can take questions before I do that. See some that. Anyway, sorry, I'll look at the Zoom chat later. I'm not able to see the window for some reason. Okay, so I'm really excited about few-shot learning for the following things. So again, like if you look at robustness and the goal of trying to get a model that works well, it seems pretty impossible to think of having one model that we a priori thought of all the distribution shifts that the model could encounter and then just deploy this model and forget about it. So it seems much more realistic to imagine that we'll make a model as good as we can, and then perhaps the world is going to change, the model is going to make some mistakes, we figure that out and we allow the model to change. So for that, what we really want is like, can the model learn quickly from just a few examples so that as the world changes or as we realize that we want to teach the model to do something, we can give just a few examples and fix it. And the nice thing is like large scale pre-training does enable good performance with much smaller amount of downstream data. So again, this like another kind of robustness goal of getting the model to adapt seems promising and seems doable with these large scale pre-trained models. And yeah, so as I said, this is useful when the world changes and we need to update the model. But like I said in the previous part, like any parameter update that we could do is potentially risky. And like we saw there, like just doing small updates of fine tuning, like running that for a few epochs, for example, or a few steps also already distorts your features. And linear probing, then fine tuning, like you can only prove some things about it in very restricted conditions, and it's possible that it's not the best thing to do. And we've actually screwed up the robustness. So any parameter update seems risky. And so one kind of, one thing can we think about is like, can we get away with no fine tuning at all? So can we just not change any parameters? And that way it's like pretty safe. So we don't have to worry about screwing things up by updating parameters in a wrong fashion. But like, how do we actually do this? Like, how can we teach a model something where we give a few examples, but like don't fine tune at all? And I guess we have some people here from NLP, but like this was very interesting to me as a machine learning person that this might actually be possible. So you have large language models. It's really exciting that they're trained to predict the next token given previous tokens on much large scale data. So that, for example, they're trained to do tasks like the following. So like, let's say like filling up something about Albert Einstein, and like, it's been trained to predict the next word, for example, given the statement. So I think I missed one of the slides in reading, but okay, the main thing is that large language models can actually do this kind of in context learning where without doing any parameter updates and just giving a few examples, you can actually make a model learn what you're trying to get it to learn. And so the question here is like, given a model that's only been trained to predict the next token, can it actually solve all the tasks? that is no, because for example, if I just say Albert Einstein was, we don't know the task that we're thinking about, whether it was that, we want to predict Albert Einstein's occupation or nationality or so on. And so let's say the model, you've deployed the model and it always predicts like, nationality, but you actually wanted to predict profession instead. So how can we change the model to do that? And the interesting thing is that by just a priori, the model doesn't know anything. And we need to specify to the model which task we want the model to do while prompting the model. And you can do this via prompt engineering or thinking carefully about how to specify the task in the prompt in natural language. And interestingly, you can also just use data to do the same without ever thinking about like what the prompt should be. You can just give a few examples of the task that you had in mind, and then the model seems to get that. So this is a very easy way of actually updating your model, because you don't even have to think about like what exactly the change is. You just show the model a few examples of the task that you wanted to do, and the model figures out what has to happen with no parameter changes at all. And so it feels like less risky for robustness or for forgetting what it has already learned. And so that's kind of why I was really excited about in-context learning from the notion of robustness as like a really convenient way of giving the model information or like few examples and allowing the model to learn from that directly. And so the main idea here is like, if you have a task, for example, of predicting nationality, you just concatenate a few different examples, and then the model would like solve the task, implicitly infer the task and would do it the right way. Whereas if you hadn't given these examples and just asked Albert Einstein was, the model could have predicted like many different things and not necessarily the nationality. Does this, I don't know if I went fast, but does this setup make sense? If there's any questions, please ask me. Yeah.
This is the definition of robustness. You mentioned that a worst case scenario, parameter robustness, input robustness.
So yeah, I never spoke about parameter robustness. Like in general here, when I'm saying robustness, I'm just talking about input robustness. So your task or your something about the inputs have changed to the model, and then you still want your model to do well. And yeah. Yes. Yeah, but we don't care about the parameters. We care about the effect the parameter changes has on like how the model predicts on inputs. So like parameter change in absolute sense doesn't make sense, but we care about like how it affects the downstream task. Yeah. So yeah, I guess that. So in some sense, we want to make sure we don't change parameters in a way that changes its behavior on inputs. Yeah, I mean, so in this part, like just take it at face value of like just trying to explore, can we ever update the model to do a task without like ever doing parameter updates, just motivated by the fact that parameter updates are dangerous. And so here, like we're just trying to see like, can the model figure out we're talking about nationality by just giving a few examples as like the prompt. So we concatenate a few examples and then see whether the model can predict nationality. So that I'm not talking about doing multiple tasks. Like this is really vanilla, but as a starting point, yeah.
Sorry, how do you find these prompts? Is it just
Yeah, so these are just random samples. So you literally take a few examples of XY pairs with the task that you had in mind. Yeah.
Oh, okay. So you're saying if you wanted to predict the nationality,
yes,
concatenate these two things.
Yeah, exactly. So yeah, that's why this is really exciting, because in normal fine tuning, what you would do is you would take these XY pairs and then like have a loss on the representations and backdrop, but here you don't have to like change any parameters or decide the loss yourself, because as we said, depending on the loss you choose and depending on how you change parameters, it's like too complicated to think about. So like, can we get away with not doing that at all? And so it feels like pretty exciting. And this is good because now we can actually try to like use this idea for robustness, because yeah, you don't have to worry about how things change. Yeah.
I had a good question. And it's, I think, more in relation to the last one. So it's about evaluation. So my first question would be that what if you had data from the target domain already? So I would imagine that if you were to use fine tuning on the target data, then you would how does that compare to fine tuning and linear probing on just the source data? And my second question was that I mean, is there, it's more like when we think about distribution shift, I would imagine in practice that a large proportion of the data would be in distribution and or only a smaller proportion of it would be out of distribution. So does the evaluation protocol kind of map that? Because I'll imagine that 99% of my data is in distribution and only 1% of the data is out of distribution, in which case some of those findings might differ.
Right. Okay. So to answer your first question, how does it compare to fine tuning on target data itself? Like, of course it does worse. Like if you don't see labels from the distribution shift, but like a few percent, I mean, I don't remember numbers, but it does do worse. And, that's you don't ever match the oracle perfectly. But in terms of the fraction of how much you care about in distribution and out of distribution, that's exactly why you don't want trade-offs. Because suppose you had a model that improves one metric, like it improves out of distribution, but at a cost of 10% in distribution. Like, should I use this method or should I use something that's more accurate and less brittle? Like those depend on what exactly is the ratio of points you see. But if you have a method that actually improves both, like that's just universally better, then you don't have to think about this, which is kind of why it is important to get something that does not compromise on one or the other. Okay, so so in this paper, like we were just trying to understand, like, why is this even possible that you can expect in context learning to work? And this is quite magical, or this was really magical to me, because usually you have to do some kind of learning and you have to update some parameters, something to tell the model about the task. But here, like the model is just doing it on its own. And in particular, like there are like two sort of mismatches that happen. So if you recall, like during pre-training, or like what the model is trained to do is to just predict the next token given the previous tokens. And so that is nothing, like it's not specifically designed to do any kind of in-context learning. So for example, you give documents like this Wikipedia article on Albert Einstein. So there's nothing that the model has to, I mean, it's not trained to ever look at a few examples and discover what the task is and then solve it. And also the prompts are not formatted like natural language. Like if you look at the example from the previous slide, you had like a bunch of different celebrities and the nationalities. And that's not the kind of natural language that the model was mostly trained on. And so given this mismatch and sort of this mystery around like why is the model able to infer tasks, so we try to think about what is the simplest setting where we can try to understand how pre-training could be related to in-context learning. And this is obviously hard to answer on real data sets because the pre-training data is really messy and it's huge. We don't have access to everything. And of course, the models are also like big, which is like 170 billion parameters when I made this slide. So we tried to think about what could be a first step for understanding in-context learning with simple framework and try to get a data set and use those insights to figure out how to design prompts. So in the interest of time, I just will very briefly talk about this model and then switch to some other things. But the main idea is that when we look at what these documents look like, we imagine that there is some latent concept that the document is talking about. So if you have this latent concept, now you condition on this concept and data is generated according to a hidden Markov model. So here's a visualization. So you sample this concept that you are thinking about or that this model is about, and then you sample text from an HMM. And the main thing is because there is this latent concept, so if a model is actually trained to do or like can fit this pre-training distribution well, then implicitly it has to infer what is this latent concept that your text is about. So if we have a concept here, for example, like some wiki bio, and then you generate text based on the concept. But if it only looks at the sequence and tries to generate the next sequence, it has to first figure out what was the latent concept that was going on, and then generate the next token via this HMM. So because of this latent concept, you're actually like all sentences share this latent concept. And this is something that the model has to discover or has to infer when it has to generate the next token. And this feels a little bit like in context learning, because if you had some task which was hidden, but you only saw examples that looked like the task, the model has to automatically infer what the task is. And you're saying that if the pre-training documents also have some such structure where there is some latent thing that ties everything in the document together, which the model has to infer when it makes predictions, and that's kind of where the model gets its ability to do in context learning from. So for example, here, if it has to like actually fit this pre-training distribution, it first has to infer theta and then generate text from HMM corresponding to that particular inferred theta. So this is like basically the main idea here. Like, for example, now if you give prompts that look like this, now the model first tries to infer like what could be the concept that ties all these prompts together. Even if all these prompts are not very likely, as long as the most likely theta star is correct, so as long as the model can infer the correct concept tying them together, then the model can solve the task. And this is kind of the main sort of like mental model for trying to think about why and when in context learning can emerge. But of course, there are a lot of bells and whistles for like actually proving how you can go from pre-training to in context learning. But the main idea is that the model is implicitly inferring something about the text, even if it has to just predict the next text. And that's kind of why the model gets this ability. Yeah, so one sort of interesting experiment, which this like mental model helped clarify, was the following. So this is from Min et al., where they found that if you just randomize the labels in the prompt that you give, the model can still solve the task well. So if you look at like sentiment classification here, so these are just random labels on the left, but then you give that to the model as a prompt, but the model actually gets the correct answers. And this is something that could not have happened in supervised learning. Like if you train with random labels, there's no way the model is going to get it right. And the reason this works here is because the model has learned some natural tasks that exist in the real world while pre-training. So it knows that there is a potential task of like classifying a sentiment. And now, given the examples that it has, like what is the most likely task that is going to come out of this? It's probably sentiment classification, because that's more like, because the model has probably never seen tests that is just random. So it now thinks that given this particular set of tokens, like what is probably happening is you wanted to do it sentiment classification, and the model gets it right. So the main thing is that, yeah, so even if these are unlikely inputs in general, as long as the model can infer what's the most likely thing you're talking about, given its pre-training, that's how the model gets its ability to do this. Anyway, so we do more connections to other empirical findings in the paper and a small scale data set for experimenting with this as well, in terms of trying to think about robustness of in-context learning and so on. In the last 5 minutes, another aspect that I'm really excited about because of pre-trained models is richer supervision. So right now, like when I started the talk, I spoke about like having this kind of mathematical characterization for what we want, but that's of course not very natural. So if you think about how do we communicate about distribution shifts, we typically maybe explain it via language, but we don't really write down like, you know, the weather has changed. I don't know what the mathematical representation for that is. So the dream is like, let's say we trained a model in California. So we have all these sunny road signs. And you just want to communicate to the model that like, I do anticipate that there are going to be snowy road signs also. And then the model can like work well. So I don't want to write down this set or like think about how to characterize it. I just want to say what I know about the world, which is that things are going to change. And I want to make the model work well on this training and this unseen domain of like snowy road signs. But to get something like this, for example, for say road sign detection, I need to have a way to combine image and language. And so that's what we try to explore in this paper with like models like CLIP, if people are familiar with, where there are models that can actually learn a joint embedding of images and language. And so the hope is that we can use that the language description, for example, sunny to snowy, to figure out like how the images might have changed. And we can hallucinate these images to get data augmentations. And it's effectively like we've trained on the unseen domain as well. So the idea is like, can we actually say what we want the shift to be, like sunny to snowy? And can I hallucinate those changes via data augmentations and solve this problem by now effectively training on that unseen domain as well? So this would be a really convenient way of getting robustness for many real world applications, because you can probably verbalize the change in many cases. And now you can use that to get like augmentations for free. And so very briefly about how these kind of image language pre-trained models work is they're trained to look at a bunch of images and possible captions and try to match like the right image with the right caption in the batch. And so that's how you use it to get this kind of joint image and language embedding space. And if you want to use it to make predictions, for example, you can give a bunch of prompts for corresponding to the particular classes in text, and then you'll use the image to see which text it closely aligns with and use that to get the prediction. And so there have been papers that try to actually do image manipulations using this image text shared space. For example, over here, let's say you want to take this image and convert it to a cat. You just mention it in text, so like dog to cat. Then you look at how much the text embeddings change, like which direction did they change, and then you just use the same change in the direction of the image space as well, and hopefully you'll get an image of a cat. And so there were all these like papers that claimed to be able to do something like this, which is really cool, where you just change things in the text space with the text descriptions, and then you somehow correctly map them onto changes in the image space as well. So this seems like it's promising now, because if I just looked from sunny to snowy and then just added those changes to all the images, then I've trained on snowy images as well. Right, so main idea is that can we transform image embeddings to correspond to changes in text embeddings? But we tried to do this because most papers claim that this works. But what we found was actually that the class consistency is not necessarily preserved. So we were able to make things look snowy, but then in the process, destroyed any information about the traffic sign itself. So this was not great. Like, so you've just made things look more snowy, but you can't really use it as a data augmentation. So all these like previous papers, like they only, like these kind of are probably very cherry picked and maybe have like artifacts that you can't pick up. But if you actually wanted to do something like this and use it for data augmentation and build a reliable classifier, it doesn't really work that easily. And so we ended up having to do some kind of a regularization using the original zero shot, or original model, which got the right classes and tried to preserve some class consistency. But yeah, so I guess like it kind of works, but not perfectly. And so hopefully as these image language embeddings get better, we might be able to do such things. And don't read too much into the results, but like basically it does improve over existing methods, but not by a huge amount, because we weren't able to like actually make it learn these embeddings in a way that preserved the class while also changing the domains in a very faithful manner. But it still improved over previous methods, so there was still something useful that was going on. And so to summarize this part, I think like robustness via text descriptions is very convenient and exciting, and again ties into the fact that we might never be able to say a priori exactly that we want what we wanted, but let's say we discovered something, can be easily communicated to the model. But to achieve this, for example, in image classification, we need reliable image text correspondences. And current models show some promise, but hopefully bigger and greater models can allow us to do these things much better. And with that, I wanted to generally summarize that this is a really exciting time to be in machine learning, because you're seeing so many great progress. But at the same time, a lot of robustness concerns still remain. So we're still not at a point that we can reliably use any of these systems, assuming that they're going to work and be robust. But large pre-trained models do open up very interesting avenues for improving robustness. Firstly, they digest a very diverse and vast amount of data, so they probably have rich information. They allow us to do like few short adaptations, so we can hopefully like allow the model to keep learning over time, and also provide richer supervision, for example, via language, to tell these models what kind of shifts to expect. And with that, I want to thank my collaborators, especially Ananya, Michael, and Lisa, who are the first authors on the 3 papers that I presented, and Open Philanthropy for sponsoring my research.